All right, hey AP Chemists. This is part of the Unit 1 important information. I'll consider this part 2. This is where we'll start talking about energy and calculations associated with atoms and molecules. So just a little bit of a brief update or reminder here, if you've never heard of it. Energy, you may have seen this in your summer work, is in the unit of joules, like I see here. Examples of energy would be like heat, like when things change temperature or when things melt or boil and you require heat for that. Or what we're going to focus on in these notes, radiation, which is like light. Light has energy, and we're going to be calculating the energy of that light, and that's definitely associated with atoms and molecules. So we're interested in how much energy is needed for chemical reactions. To make measurements of many properties, we require the approach of spectroscopy. That is when we add energy to atoms, and I have like a little schematic here. We add energy to an atom. Let's pretend like this red circle is an atom. Something's going to happen to it. Either it'll react, it'll gain or lose electrons, it'll just move, and then if it has some excess energy, it'll release that or emit. And we could calculate the energy that's associated with this light. We have some equations here that we're going to be introduced to. So here's our first equation for calculating energy. Energy E. This is E is equal to H nu. This thing looks like a V. It's the Greek letter nu. It is part of the Greek alphabet like alpha, beta, gamma. You may have heard of this in math class. If not, it's okay. I'm introducing it to you. The Greek letter nu looks like this weird V. Nu is what's known as the frequency of light in either something called per seconds or hertz. Frequency is how often light occurs per second. So that's why it's up per second. So if I want to make a little note what frequency is a amount of light per second. And that's why it's 1/second, or what we see is s to the minus first. That's the same thing as saying 1/second. Another unit of frequency that you may have heard of is something called the hertz, Hz. What's pretty nice is 1 per second is equal to 1 hertz. So I could easily convert between the two. And then we have a constant that is something called Planck's constant, H. That's just a letter. Planck's constant is 6.626 times 10 to the minus 34th joules times second. That's a multiplication dot. And so if I ever want to calculate energy, I'll take this H, multiply it by whatever frequency I get in nu, and that's going to be my energy in joules. So just kind of, we'll do equations and calculations later, but if I have the frequency of light, right, if I say that my frequency is, 560 per seconds, I would multiply that by H, and then I would get my energy in just joules. So just doing a quick example there. Now, it's not typical to use frequency. Sometimes we use something else called lambda, which right here is the wavelength. This is lambda, which is the wavelength of light, which is how long the light is. So we have frequency, which is how much light we get per second, and then we have wavelength, which is exactly how it sounds, how long the wave is. If I want to go from wavelength to frequency in order to calculate energy, I have this equation. Frequency times wavelength is equal to something called c, which is the speed of light in meters per second. I could rearrange this equation where I could say, okay, if I want wavelength, it's going to be equal to the speed of light over nu, or frequency. Or if I want the frequency, it's going to be equal to the speed of light, which is a constant, and I divide that by wavelength. So these are important equations for us, that if I have a certain amount of light, I'm able to get wavelength and frequency. If I multiply, I'm going to go back here, if I multiply H times frequency, I will get my energy. If I don't have frequency and I have wavelength, I could just take the speed of light, which is 2.99 times 10 to the 8th meters per second. That's a speed, how fast something is going per second. I divide it by the frequency, and that will give me my wavelength. The wavelength will be in units of meters. okay? So that's very important for us here. So just talking about these equations here, I have 2 to 4 different equations here. I'll just label them with A, B, C. I have E equals h nu. I have frequency times wavelength is equal to speed of light. I could break that into B1 and B2. I could take wavelength is speed of light divided by frequency. Frequency is speed of light divided by wavelength. Good job. Now I could combine some equations here. If I were to combine, and I'm going to use a different color, if I were to combine this equation with this equation, we will get a more useful relationship. Why is it useful? Because we're typically given the wavelength. It's not often that we're given the frequency. So since we're typically given the wavelength, I could say E is equal to hc divided by lambda. That was horrible. I'm going to rewrite that just because of my handwriting and a little OCD here. hc over lambda. That's a little bit better, right? And I'm still calculating E energy. This gives me energy in joules. H is going to be in the 6.626 times 10 to the minus 34th joules times second. C is the speed of light, which is typically 2.998 times 10 to the 8th meters per second. Wavelength has to be in meters, like I mentioned earlier. Now I have a little conversion here. The wavelength of visible light is typically in nanometers to us, another conversion. 1 nanometer is 10 to the minus 9th meter. So I could do conversion factor and dimensional analysis. Let's say I was given 580 nanometers, just as an example. I could convert that to meters by putting nanometers on the bottom, meters on top, 10 to the minus 9th over 1. Boom, this is 5.80 times 10 to the minus 7th meter. So I just did a quick little calculation here, just showing you an example of converting between nanometers and meters. We could do more in class. These conversions were found in our summer work, part 1. Eventually, I'm going to ask you to memorize this conversion. Make sure you know how to go from meters to nanometers. You will not need to memorize Planck's constant. That's given to you. You will not even really need to memorize the equations here because they'll be given to you. Now, notice how I said this energy is in just joules, a unit of energy. Sometimes you'll need the energy of a mole of photons. Oh, I forgot to mention the word photons. I'm so sorry. So what's a photon? Well, I've talked about all this light and energy associated with light. Well, a photon is a lump of light. Light can be related to energy. That light that could be added or removed from atoms or added and come out of atoms, we call that light energy. We call that photon. A photon is a light energy or a lump of light. So now this is joules per photon for just one photon, right? So if I were to calculate this energy would be joules per one photon. Now, if I wanted a mole, and I don't know why this got all messed up here, and I'm sorry, 1 mole, we should remember from beginning of this year and our summer work, 1 mole is 6.022 times 10 to the 23rd. So if I want 1 mole of photons, that's 6.022 times 10 to the 23rd photons. What I could do is I could take this equation that I have above, hc over lambda. This is going to be giving me my energy in joules. If I want joules per mole, I would have to multiply this by what I like to call Avogadro's number, Na. That's this business here. So if I multiply the energy that I get from the equation hc over lambda, if I multiply it by Avogadro's number, I will get my energy in joules per mole. That is my energy. Okay, so just talk through some calculations here. Something else to note, and this is from your summer work, 1,000 joules is 1 kilojoule. So you could always do a little bit of conversion there. If I have 5,805 joules, if I divide by 1,000 or times 1 kilojoule over 1,000 joule, I'll get 5.805 kilojoules. Just another little example of converting for us. These sets of notes are very heavy in calculations. And so I want to check to make sure that you could do these calculations. I have the answers here for A, B, and C. On your own, I'm going to get a set up, but on your own, I just want you to plug and chug. Plug and chug. And so I'm going to set us up, and then I'm going to end the lecture here. Example A says, calculate the energy in joules of a photon of red light having a frequency of 4 times 10 to the 14th hertz. Okay, well, I want energy. I was given frequency, which is nu. Well, I know the equation I have to use is E equals H nu. H is a constant. That's right up here. Nu is right here. Don't forget that 1 hertz is equal to 1 per second. So I'm good to go here. See if you could calculate it and get the answer here. So the problem that students typically have is plugging and chugging and getting the right number. It says convert this frequency into wavelength. So it wants the frequency, which is nu, 4.00 times 10 to the 14th hertz, which is the same thing as 4.00 times 10 to the 14th per second. Convert it into wavelength in nanometers. Well, the equation I have to use, if I take my speed of light right here and divide it by the frequency, I'll get my wavelength in meters. So if I want my wavelength, it's going to be the speed of light, divided by my frequency here. And then I have to do another step. 1 meter is 10 to the 9th nanometers, or if you don't want to use that, you can use the one that I gave to you. 10 to the minus 9th meters is 1 nanometer. It doesn't matter what you use. You could do the calculation up here. This step will give me my answer in meters, and then I have to convert that to nanometers. See if you get 750. And then finally, with the answer that you get in A, what is the energy of 1 mole? Well, with the answer that you get in A, you take your A energy, and you're going to multiply it by Avogadro's number. See if you get 160 kilojoules per mole. Well, if I first do this, this is going to give me joules per mole. If I want to convert to kilojoules, I have to divide by 1,000. Or I do that business up here. If I have my joules, multiply by 1, divide by 1,000, that's going to give you my answer in kilojoules per mole. So end this lecture with making sure that your work in our setup here matches these answers. And then try on your own sample problems 1 and 2. These you'll need to turn in 4 points. Alrighty, so that's it. So we learned about 3 to 4 equations here. We have E equals H nu, very important. We have nu is equal to C over lambda. That helps me go from frequency to wavelength and vice versa, or wavelength to frequency. If we combine those two, I'll get E equals HC over lambda. That helps me get my energy if I know my wavelength. That's it. And then finally, if I multiply by Avogadro's number, that's 6.022 times 10 to the 23rd, I'll get my energy in joules per mole. I also showed you how to convert nanometers to meter and joules to kilojoules. This is just a refresher from our summer work. If you have any questions or concerns, we're definitely going to do more calculations in class. Take this as our beginning introduction to using equations and plugging and chugging.